My name is Aloni Cohen, and I'm going to tell you about joint work with Kobbi Nissim towards formalizing the GDPR notion of singling out, which recently appeared in the Proceedings of the National Academy of Sciences. There's a problematic conceptual divide between data privacy laws and data privacy techniques. The laws which tell you what you have to do and the techniques which tell you what you can do. Laws are typically imprecise and open to interpretation. Techniques are usually more precise and come with mathematical guarantees a lot of the time. But what we need is not mathematical guarantees, we need legal guarantees. So this leaves unanswered the question whether a given technique satisfies a given law. And this is the question that we're going to think about in this work. And the approach that we take in this work is to move back and forth between legal analysis and mathematical analysis, and to have each transform into the other. So we start with legal text. We look at the laws, we look at guiding documents, understand and extract the relevant text, and then formalize that into some mathematical understanding. Once we have a mathematical model, we can analyze the math alone in relation to other notions, and then ultimately draw legal conclusions. So that's at a high level what we do in this work. Specifically, we do it for this concept called singling out, which comes from the GDPR, and we extract from the legal text a mathematical notion that we define that we call predicate singling out, which we'll analyze. We'll see that how it relates to differential privacy and K-Anonymity, and then ultimately we'll try to draw some legal conclusions. So let's begin with the first step. The GDPR, the General Data Protection Regulation, basically is the omnibus privacy law in the European Union, went into effect in 2018. It governs the processing of personal data. So personal data, this Article 1 is the text of the legislation. And Recital 26, recitals are like a preamble, in a way, to the legislation. Recital 26 makes clear that the law does not regulate personal data that's been rendered anonymous. So only if it's personal data is it regulated. So this suggests the following sort of a picture, that you can take personal data and put it through some magic box M, and out comes anonymous data, personal data rendered anonymous. And the question that we tackle is, what does this box M have to do in order for its output, M of X, to be considered anonymous? So we have to define personal data. Article 4 of GDPR defines personal data as any information relating to an identified or identifiable natural person. And Recital 26 elaborates, saying that account should be taken of all the means reasonably likely to be used, such as singling out to identify. So singling out is one way of identifying. There are others. And if you can identify, then it's personal information. So anonymization requires that you must prevent singling out. Now, we turn from the text of the GDPR to some guiding documents. In this case, we're looking at a document put out by the Article 29 Working Party, which is some document group that provided guidance to a predecessor of the GDPR, but which had similar language. And the Article 29 Working Party clarifies that a person is identified within a group of person when he or she is distinguished from all other members of the group. For instance, by specifying criteria which allow him to be recognized by narrowing down the group to a single person. So it suggests something like the picture on the right, which we're going to call isolation. So isolation refers to you have a data set of personal data X, some criteria P for predicate, and then the predicate should have one match in the personal data, and if it matches a single person, then you've succeeded. So this idea that singling out is the same as isolation is what we interpret the Article 29 Working Party to be suggesting, and has also been made explicit in prior work by Francis et al. Now, we're going to push this intuition and see that it's not good enough for our purposes, and we're going to elaborate on it to derive predicate singling out. Our goal is to define predicate singling out so that for a mechanism to be considered a general purpose anonymizer under the GDPR, it must prevent predicate singling out. We just saw that to be an anonymizer, you must prevent singling out, and we want it to be the case that preventing singling out implies preventing predicate singling out. This means that negative results are the most legally meaningful, because if we can show that a mechanism enables predicate singling out attacks, then the conclusion is that it can't be a general purpose anonymizer under GDPR. So let's explore the idea of singling out as isolation. So what's isolation? Isolation requires outputting a predicate, a set of criteria for which there's exactly one person in the database that has the attributes. So for example, if this is a data set, there's one person who rated the movie Crash a 4. There's one person who watched Mulan in February. That's the second row. And there's one row that doesn't satisfy each of the other two criteria. That's the third row. So this is our schematic syntactic picture. We're going to look at a data set. We're going to call it X and assume that the data set is drawn IAD from some distribution D, and the data set is of size N. So again, I want to emphasize that our modeling choices are targeted towards the idea that negative results are going to be more legally meaningful than positive results. So making this restriction that the data set is drawn from a distribution does weaken the definition of security, but it strengthens negative results. Okay, moving on. So we have a data set X. We're going to feed the data set through an anonymization mechanism M, which outputs something, M of X. It could be interactive. Here, we're doing things non-interactively. M of X is given to the adversary A, and the adversary outputs a predicate P. The predicate P operates on rows, like potential rows of data X. And the adversary doesn't get any input except for the output. It doesn't know anything else about the data X, but it does know the distribution and the size of the data set. So the adversary's goal is to output a predicate matching exactly one row in the data. So we could define security against isolation, a mechanism secure against isolation, if no adversary can succeed except with negligible probability in winning this game by outputting a predicate that isolates. So the problem with this definition is that it's impossible to satisfy. In particular, there's a trivial attack which doesn't even require looking at the published output at all. So the adversary can output a predicate P star, which matches a one in n of the people in the distribution. So for example, if the data set is of size 365, then P star could be born on February 2nd. And if the birth days in the data set are uniform, then you expect that this predicate matches exactly one person in the data set. In expectation, the predicate will match one person in the data set, and the probability that it matches exactly one person, you can work it out. It turns out to be close to 1 over E, which is 37%. It's a little less than 37%. And you can do this. The adversary can do this without actually knowing much about the distribution, except that it has been entropy by using hashing, for example. So that was a trivial attack. So what makes an attack non-trivial? So one example is if the adversary was able to output a predicate, like born on February 2nd, but instead of 37% probability of success, the adversary had 97% probability of success. If the adversary could do this, then it can't do this by accident. It can't do this without looking at the data, and therefore there's something non-trivial going on. There's some disclosure happening by the mechanism. So this suggests that improvement over some baseline is what matters. But it would also be non-trivial if the adversary output the predicate. There's one vegan Colombian Jewish pilot who's fluent in Dutch in the data set and managed to use that to isolate somebody in the data set, even with 10% probability or even maybe 1% probability. Because this predicate is so rare, you don't expect even one person in the data set to satisfy this predicate. And so this suggests that the baseline that we have to compare against, that we want to compare against, depends on how rare the predicate is in the underlying population. So we're going to use these two ideas. First, before we make it formal, we need some notation. We define the weight of a predicate as the probability over drawing a random row from the distribution that the predicate, that the row satisfies this predicate. We define a success probability, which is for any fixed adversary and distribution mechanism M, a number of rows n, and weight W, which is the probability that a predicate isolates a data set, isolates a row in a data set, and the weight of the predicate is at most W. And this probability is taken over the experiment where we draw a data set X, IID from D. We give it to the mechanism M. We give the output of the mechanism to the adversary, and the adversary outputs the predicate. The baseline is defined as the best success probability that any trivial adversary can achieve. A trivial adversary is one that doesn't look at the mechanism's output. And it's not too hard to show that the baseline has this form. So it's maximized at 1 over n when the weight is 1 over n. And as the weight gets smaller, the baseline drops off. And in particular, when the weight is negligible, the baseline is negligible. That means that a trivial adversary has a negligible probability of isolating with negligible weight predicates. And that's what we'll compare against. We can look at high weight predicates too, but we won't for this talk. So now we're ready to define predicate singling out. So the adversary's goal is to output a predicate P of negligible weight, matching exactly one row in the dataset X with non-negligible probability. Correspondingly, we say that a mechanism M is secure against predicate singling out if no adversary can succeed in this game except with negligible probability. So here it is again more formally. M is PSO secure if for all negligible W, for all distributions D, and for all adversaries A, the success probability is negligible. Now we also consider a parameterized definition for epsilon and delta constants, and for any W less than 1 over n, we say that a mechanism M is epsilon delta W PSO secure. If for all weights W prime less than W, the success probability doesn't increase too much over the baseline. So it's bounded by e to the epsilon times the baseline plus delta. We'll mostly consider the simpler definition above, which only considers the negligible weight predicates. Now that we've defined predicate singling out, let's analyze it. So the first question is whether there is any mechanism that is PSO secure. So we'll consider this counting mechanism, which is defined for a predicate Q, and it returns the fraction of the data set that satisfies the predicate. It gives you an exact count. So this mechanism, for any Q, the counting mechanism is PSO secure. And this follows from the observation that the counting mechanism can only output n plus 1 distinct values, and which implies that a trivial adversary can emulate any strategy that depends on the output of the mechanism just by guessing the output and running the other strategy. And so the difference between this trivial adversary and that strategy that it's emulating can only be a factor of n. Now it's a simple mechanism, it's a simple argument, but it gives us two implications. One is that PSO security doesn't imply differential privacy. The counting mechanism is deterministic, and differential privacy requires randomness, so it's not differentially private. And the second, as we'll see next, it implies that PSO security doesn't compose. So a good property that we'd like of a security definition is that it composes, which is to say that if we have L mechanisms that are individually PSO secure, then those L mechanisms considered together are also PSO secure, potentially with some degradation in the parameters. In the paper, we show that PSO security doesn't even compose twice. But now I'll outline a proof for a weaker result, which is that PSO security doesn't compose superlogarithmically many times. So we'll consider a data set which is drawn from a distribution where every row is just binary data drawn uniformly at random. So every bit is 0 or 1 with 50% probability. And the observation is that if we have a counting mechanism with predicate Q1, where Q1 isolates a row X, then we can define a bunch of other predicates. We can define a bunch of other predicates to let us learn the bits of X. And so Q2 is going to be the conjunction of Q1, and the predicate that guesses that the first bit of the row is 1. So depending on the output of Q2, we learn the bit of Q1, assuming again that, depending on the output of Q2, we learn the first bit of the row X that Q1 isolated, assuming that Q1 isolated a row. Continuing in this way, we can learn the bits of this row X one by one. After we've learned L bits, the weight of the predicate that this gives us is 2 to the minus L. If L is superlogarithmic, this is negligible. But still, this attack required that we had a predicate Q1 that isolated a row. And we still haven't said where we get that. But the whole discussion of the baseline and the trivial adversary tells us that it's easy to come up with such a predicate. So take Q1 to be the predicate P star, which is output by the trivial adversary. Predicate has weight 1 over n, and it has a probability of 1 over e of isolation. So pick a random, take Q1 to be a random trivial adversary predicate, P star, and then Q2 to QL correspondingly. You can amplify this so the probability of success approaches 1. Now, we saw that PSO security doesn't imply differential privacy, but the reverse is true. If you have a differentially private mechanism, it's also PSO secure. In particular, if you have, for any weight, it's little o of 1 over n, and then the epsilon from differential privacy becomes epsilon plus little o of 1 in the PSO security definition. And if we're using approximate differential privacy, so there's a delta. If delta is negligible, then it becomes negligible in the PSO security definition. The proof of this theorem is by results that connect differential privacy to statistical generalization. So you can view predicate singling out attack as a type of overfitting. The predicate has to isolate in the row, which means that P applied to X gives you 1 over n. That's isolation. But it also has to be low weight. So the P of D, which is the weight of the predicate, is little o of 1 over n. And this gap between little o of 1 over n and 1 over n is a type of overfitting. It's a type of overfitting which is prevented by differential privacy. Finally, we'll turn to K-Anonymity. So K-Anonymity is probably best described by example. So here's an example of a K-anonymous mechanism where the data, which is on the left, is sampled uniformly, say, from a domain of size 2 to the n. And K-anonymity requires that that in the output, every row belongs to an equivalence class or a chunk of k rows. And these k rows should all be indistinguishable from each other if you only look at the output. So in this example, k is 3, and the K-anonymizer is just outputs these intervals of the rows. So the first 3 rows, 1, 8, and 27, on the output side get transformed into the interval 1 through 27. Oh, and as you can already see on the slide, I spoiled it. This is not PSO secure. So in this example, this mechanism reveals 2 rows per each one of these chunks. So for example, an attacker can look at the output and output the predicate, which outputs 1 when x is 343 and outputs 0 otherwise. This predicate matches exactly 1 row in the input, unless there's collisions, which happen with very small probability. And the weight of the predicate is 2 to the minus n. So this has successfully predicate singled out. So this is one sort of contrived example. It turns out that K-anonymity enables predicate singling out more generally. So if you look at a K-anonymous mechanism, generally it outputs these chunks which are defined by some predicates themselves. So I'll call these predicates phi. These phi have to match k out of n of the input data set. And typically the phi will match about k, not much more than k. And also, if you have high dimensional data, K-anonymization algorithms like to keep as much of the richness of the data there. And these predicates phi are going to be very low weight. So if the K-anonymizer is such that the phi, these predicates phi are negligible weight and output and match approximately k rows of the input, then there's an easy attack. So the attack, recall that the trivial adversary could just output a predicate that matched 1 over n of the data set and manage to isolate within a data set of size n with probability 1 over e. So now what we're going to do is we're going to do the same thing, but instead of targeting the data set of size n, we're going to target the equivalence class of size k. So the weight of this predicate is smaller than the weight of phi, which we're assuming is negligible. And this predicate isolates if this predicate p star sub k isolates within the chunk defined by phi. To prove that this happens with about probability 1 over e, just like the trivial adversary and the baseline, but to prove that actually requires a bit of a careful argument using conditional min entropy. Now that we've extracted legal text and we've come up with a mathematical definition and we've analyzed it, let's draw legal conclusions. So first, we saw that singling out as isolation doesn't really make sense. If an attack is possible without looking at the mechanism, it's not an attack on the mechanism. So some notion of a baseline and incorporating probability seem to be integral in a meaningful conception of what singling out means, and even that's in prior legal writing. Going to our more concrete theorems, we compare our results to the findings of the Article 29 Working Party, which issued an opinion on a predecessor to the GDPR that said, for example, that K-anonymity prevents singling out and differential privacy may not. We think these findings need to be revisited. So going through our technical results, we saw that K-anonymity doesn't prevent predicate singling out, and therefore we conclude that K-anonymity doesn't prevent GDPR singling out. So it doesn't make for a general purpose GDPR anonymization tool. We also saw that PSO security doesn't compose, which suggests to us that preventing GDPR singling out probably also doesn't compose. And so singling out the GDPR notion is probably not sufficient as a standalone security notion. We also saw that differential privacy prevents predicate singling out attacks, which is maybe some evidence that differential privacy prevents GDPR singling out attacks. Ultimately, what we'd like to know is what it means for something to anonymize in the GDPR. But that seems like a good direction for future work. Thank you.